Hello.
Welcome back to the afternoon session. Just a quick comment. The photos that we took yesterday, they're on the webpage. So if you look at you can find them there. And now let's listen to John.
Okay. So, thank you. This is my third lecture. So congratulations to Roger on the year for being done. You're a lot in there, a little bit behind us. The lecture was titled Galois about Eigenvarieties, and that is what I will talk about. But I'm going to sort of split that topic over this lecture and the next lecture. And I'm also going to split the applications and open questions I had in mind for the fourth lecture over this lecture and the next lecture. The first thing I want to do right now is I want to make just a review and a small cleanup of what I said last time. And also I've been holding on to this P as 11 example and like level 1 kind of things. I want to state things at least in a form that you can take to a paper and read if they don't choose P as 11 in the paper. So I'm going to use a prime P and a number N and things like that. So space I have. N is going to be an integer at least 1. And I'm going to state some GLN things. So eventually I will move beyond GL2. But N is at least 1 and P is going to be a prime number not dividing N. You can think of P as the fixed thing and N is maybe what you're varying you want, or the other way, depends what kind of problems you're trying to solve. And always R is going to be K minus 2, which is a non-negative integer. So K is like the weight of a modular form, and R is this power of the symmetric power that you take when you construct homology on the modular curve. Yeah, so maybe I'll just write it over here. So what I was talking about, or what Roger introduced, was the cohomology on the modular curve, y gamma 0 and P. So that's my level, it has a P in it. And then there was this MR, and there was a plus or minus. And here, this MR is sim R with some coefficients, maybe a field or maybe ZP or something like that. And inside here, once you fix the sign plus minus, you have the weight K cusp forms of level gamma 0 and P. If I decorate the cohomology with something here, then you'll get a nice isomorphism. And this map here, I'm just going to denote by F goes to Pf. And then also last lecture, I talked about a third object that fits into this picture, the cohomology at level gamma 0 and P with coefficients in D lambda R. So I am going to take Mladen's choice of calling weights lambdas now. Okay, and lambda R here is an algebraic character on ZP cross that's just raising to the rth power. And I constructed a map for you on the level of coefficients, which induces a covariant map on cohomology. In the entire picture, there's Hecke operators acting. So T is going to be my notation for the QP algebra generated by the Hecke operator UP and the TL, where L does not divide NP. So that acts on the cohomology here, it acts on the cohomology here, it acts on the space of cusp forms here, and all of these maps are equivariant for the T action. And one thing that does come up in this theory is that when you have a space of modular forms, of a level, and you take a prime P, like the one here, that divides the level exactly once, then the action of the p-adic operator, UP on this vector space, never has the eigenvalue 0. So this has non-zero eigenvalues. Okay. Good. Is that all I wanted to say? One more thing. Let me make a remark now over in this space. You can arrange your notes however you want, but I have some space here. The remark I want to make is that the other thing I explained is that when you take this cohomology, the d lambda coefficients, this makes sense for lambda in W, which are the continuous Homs of dp cross, valued in the multiplicative group of whatever coefficients you want. And it's just when you take a p-adic weight that happens to be an algebraic weight, then you get these extra objects. So somehow this thing exists for all sorts of weights. Any questions about the objects on the board? That's just a brief review and clean up our organization of the different objects that we have going on here. Good. So then the theorem, let me be even more precise here. I think I called this an eigenvariety, which isn't really fair. Let me call it an eigenfamily this time. In the sense that I'm only constructing a small affine piece of an eigenvariety. Okay, so some local chart maybe. Theorem. So the primordial object I start with is a weight K-cus form of level NP. Remember, P divides N not. It doesn't divide N, so it divides this exactly once. And I assume that it's an eigenform for all the Heck operators, normalized to have constant term 1, not constant term, Q term 1. Then there exists, and I put dot, dot, dot. So this is kind of the thing of actually, there are just two objects, and those two objects have interactions. So that's the kind of theorem this is. The first object is a geometric picture. So V comes with a map that's finite onto something called U, and U is an open subset of the weight space. Open, like that. So that's the first object. And the second object is an algebra map, T, call it psi. Give more space. So it's a map from the ring of Hecke operators, kind of the abstract ring of Hecke operators, valued in the ring of analytic functions on V. Okay, and we have been talking about this a little bit in the little chats between lectures. U is some open inside some unit of open disk, so that's kind of intuitive. V is this abstract thing sitting over it. Maybe V is a rigid analytic space. It's a p-adic manifold, if those words didn't make sense to you. And this is the ring of analytic functions on this. So the first data is some object V that lives over a part of the weight space. And the second object is a way of assigning to a Hecke operator an analytic function on V. Okay. Good. So then the conditions. Actually, I have a zeroth condition, I guess. Is that F is in the theorem, right? Okay, so my first condition actually is that there's a unique point VF lying inside V. I call it VF, and it's going to map down to lambda R inside the weight space. And then that'll come up in the actual conditions I write. So condition number 1, I can't use 1 and 2. I use A and B, and C, and so on. Condition A is one that Adam pointed out at the end of my lecture that I didn't write before, but I'll kind of emphasize it now. When you take psi and you plug in the Heck operator UP, this is an element of gamma. This is an analytic function, but it's actually a unit, which is to say that it's non-vanishing on V. Okay. Condition B is that if you take a point V and B, little v and big V, then when you take the cohomology of d lambda v, so that means you take the point B here and you take its weight here, and you take the eigenspace for psi v, and this is non-vanishing. And here, the psi v is what happens when you take an analytic function and you evaluate it at V and you pre-compose it with the psi. Okay, so psi associates to each Heck operator and analytic function on V, and psi v is what happens when you evaluate those things at V. Okay, and this means take the subset of this cohomology where the Heck operators act through those set of eigenvalues. And then part C is where the VF comes in. So at V is VF. The action of T on phi F, or the action of T on F, if you like, is what happens when you take the value of T under the Heck eigensystem and scale by phi F. So phi F is automatically a Heck eigenvalue. And all I'm saying here is that the system of eigenvalues you get is the one from psi. Okay. And then D is that if V prime maps to lambda R prime in U, with R prime bigger than R. Oh, sorry, I forgot to say this is for every Heck operator in my Heck algebra. Anyways, if I have this weight bigger than that weight, then there exists an F prime that's a weight R prime plus 2 eigenform of level gamma 0 NP, such that this equation right here holds for F prime and B prime. So I guess it's the action on F prime this side V prime of T. Okay. So this fourth point is saying that, or the third point is saying that my kind of analytic system of eigenvalues hits the ones for F at the point corresponding to F. And this is saying that actually, if you take now a point in the weight space that's algebraic and sufficiently large, and you lift it to a point up here, then that will also give you a system of eigenvalues this way. And that system of eigenvalues actually corresponds to a cusp form of that weight. Okay. Questions?
Can you just go back to the last part out again?
Yeah. Let me draw it maybe with green what I'm talking about. So the statement starts with if V prime goes to lambda R prime. So what I'm really starting with is lambda R prime here. That's an algebraic weight. That's just a little bit larger than R at least. Okay. And this also means that there's a congruence between R and R prime because U is some little open and there's a p-adic topology on U. And so R and R prime have to be close p-adically. So this is like weight 12. This is weight 25 million, but 12 and 25 million are congruent mod p to the billion or something. I don't know. Like that's the kind of thing that's going on. Okay. Probably not p to the billion because p to the billion is probably much larger than 25 million. So okay, but I think you get the idea. Okay, and then I'm saying there's some v prime up here. Okay. Yeah. Actually, the same thing is like for every v prime up here. So maybe there's more than one. Maybe there's only one. I don't I don't know. But if V prime maps to this thing, then there actually exists a cusp form whose system of eigenvalues is the one you get from evaluating at V prime map.
Via the function file we've already set up.
Yeah. So part B is saying that that system of eigenvalues appears in the distribution value cohomology. And what part D is saying is that at certain weights and certain points above those weights, it doesn't just appear in that giant, well, I didn't really say this before, but it's a giant infinite dimensional vector space. It appears in the finite dimensional quotient arising from a classical thing.
Okay.
Yeah.
So these five. So wait, did you define what phi prime is?
Yeah. So then phi of f is the cohomology class in the classical thing.
Okay.
So f is a cusp form and phi of f is just my notation for the thing
I
in the
see.
cohomologies.
And then.
And it wouldn't hurt, like I wrote the map this way,
Okay,
but
so
it's
you're saying the heck action on that is coming from this map.
yeah.
Okay.
I'm saying that, yeah, this is an analytic function. For each heck operator, I get an analytic function. And at many v primes in the domain, I'm recording systems of eigenvalues associated with classical modular forms. Let me draw a picture. So the picture I want to draw looks like this. So that's my disk of weights. Okay, I'm sorry, Joseph. You're asking me about this. This is a one-dimensional space, like the weight space. And so I draw it as a line in this case. Inside the weight space, I have my point lambda r corresponding to the algebraic weight. And what do I also have? I have an open set U. So that's like an interval. Okay, like drawing it like a real number kind of thing rather than a p-adic thing. Then there's something else called B. Maybe B has to be like, I don't know, there's some dots maybe going like that I'm not sure whether they exist or not. But this is my B. It's some geometric object that lives over U by some map. Lambda. Up here, above lambda r, I have some point Bf. And when I evaluate my heck operators at Bf, I get the system of eigenvalues for f. Also, for any point lambda, I get some point B, and that's some object. But that's some object. There's just points. One more second. And then part D is saying that if you take R prime, where here R prime is going to be congruent to R mod P minus 1 times P to the 10,000 or something, however small you need to do to get into this little open set, then there's a point here that's Bf prime for some other eigenform F prime. And these things appear in classical spaces. This stuff involves non-classical spaces. H1 ... d lambda only. Okay, Henry, you got a question?
Yes.
Yeah.
So the Hecke action on these V's is given by that map that we got as part of the theorem, right?
Part of the data of the theorem, yeah.
Okay.
Yeah. Exactly. And that's the rough picture. That would be the picture if this finite map wasn't just a finite map, but like a one-to-one map, basically. Which is, you can just completely think of that situation. But conceptually, I want you to separate the weights with the eigensystems. That's why I call them two different objects. Okay. So that's one picture. This is pictures. There's a second picture. Let's look at the following. So I still have my F in my theorem, right? The F came as part of the theorem, and the V belongs to F in some sense. So I take rho bar, which is rho bar F, which is the Galois representation valued in GL2 of FP or FP bar however big you need the coefficient field to be to define the mod p-Galois representation. Then I previously had said something about a deformation space x rho bar. And x rho bar is a three-dimensional space over QP. I think I had it over ZP before, but now I'm doing p-adic geometry and I invert P. And I will make a correction. I think it was Henry actually who asked me about this, but maybe it was someone else. I think in the first lecture I said that it embeds into three space, and I was wrong. Okay, I made a mistake. It's almost always isomorphic to three space, but when it's not, all you can say is that it's three-dimensional. But there could be different components, and it can have singularities and things like that. Okay, I mean it can have singularities because there could be components crossing. But it's basically three space, and if you just think of three-dimensional space, that's enough. Let me draw a three-dimensional space. That's three-dimensional space. And remember that the deformation space are the characteristic zero objects that give rise to that mod p-Galois representation. One of those objects is called rho f. So I'm going to put rho f in my picture at the origin. So this is some representation valued in GL2 QP bar that reduces mod p to this thing, which means you conjugate it to take an integral lattice and then you reduce that lattice. Previously, I had constructed some objects inside this deformation space that was like rho f twisted by this kind of universal deformation of a character. Okay, that was for my first lecture. And so what I've done to this point.
Make a straight line for this one.
You want me to make it a straight line? Yeah, that's probably better. I mean, maybe I will. I was showing this to someone yesterday. Zach, right? Zach, yes, okay. Yeah, so let's just call this axis right there, that twist. Okay. What the theorem is saying now is that I have a geometric space V, but in that geometric space, I have a bunch of points corresponding to cusp forms. And each of those cusp forms has, by the theorem I stated in the first lecture, that in this case is proven by Eichlitz, Shimura in way 2, and Deligne in general, they have Galois representations. And so in my space, I have some, what color did I use? I used yellow. Maybe I should use yellow to connect it. I have Galois representations in my space. I don't actually know where they are. I'm not going to assert that they lie in a straight line this time. But these are like rho f primes, where the v f prime is v prime lies in V. And there's some countable collection of them. And they're getting very close to my rho f actually, like, because there's some p-adic variation that's related to congruences, and the closer I am in the deformation space, the more and more congruent I am. That's where we are as of the statement of this theorem. So now questions. Okay, so now in my deformation space then, I have one dimension that I've explained by the twisting. I also have this kind of yellow countable set of points. And I could take something like the closure of those things and I'll get a new dimension. I want to say it a little bit more precisely than that, but that would give you two dimensions, and I still have to explain the third one. And before I do that, I want to do some homework to help you better understand the next lecture on p-adic L functions. I want to say a little bit about how you prove this kind of statement, okay, and a little bit about the case of GLN. So the proof of the statement is not is a challenge to summarize, I would say. So let me tell you a couple things you do. The first thing is that you forget about thinking about a weight as a single object, and you think in families. You think of an open set of weights like my U. So in fact, the first point is that you can take an open set U and W, and you can generate locally analytic functions CP valued in the ring of analytic functions on U. Okay, so you can do that. And from that, you can construct distribution models, not for a single p-adic weight, but a whole open set of p-adic weights. And what I mean by you can do that, I mean like take the formulas I wrote down and replace all the fields with rings of functions on an open set. And then check a bunch of theorems about radiuses of convergences and stuff like that. And this is like, think of U goes to the distributions as a sheaf on W. Okay, and the only reason I'm putting quotes in there is it was a little bit late when I was writing this, and I wasn't sure whether I should first fix a radius of analyticity before writing that kind of statement. But okay. That's kind of a technical point. The second thing I want to say about the proof. So first of all, you forget about weight by weight and you build entire families of weights and entire families of distributions over those weights. And the thing you really need to prove is, or the one thing you need to prove is something like this. So given F or phi F, then there exists a U containing your algebraic weight. That's going to be the U from this theorem. And inside the cohomology, with du coefficients now. So this is, D already creates some infinite dimensional problems, and you're tacking onto it a ring of functions on an open p-adic ball. So this is like really kind of infinite dimensional. But given F, there is a U, and there's something inside it that I'm going to call mu. Okay, that depends on F. So maybe there's a tiny F there in your notes, but I won't put it in my notation. Such that mu is not one of these infinite dimensional objects. It's something that's a finite flat module over the ring of functions on U. And it's finite flat. Finite projective, finite locally free. Well, I guess since I'm choosing U, I can make it finite free over U if I wanted to. It's finite flat on U. This is a U module, an O module. And the second thing is that if lambda is a weight in U, then inside the d lambda cohomology, so I specialize to a weight, I'll have like the m lambda, which is mu tensor L lambda over U. That's a finite dimensional L vector space, right? Because I have a finite model over OU and I specialize to a field, so I get a finite dimensional vector space over that field. And UP acts on this. Oh, I should have said it's T stable. Once T is T stable, I can see how UP is acting. And it acts through eigenvalues whose norm, depending on alpha, is the same as the p-adic norm of my original modular form, which is a non-zero number. Okay. So those are two ideas of things you might want to prove, and I hope that it helps understand a little bit of what's going to go on with p-adic L functions. Let me connect it to my second lecture. In my second lecture, I sketched this argument of eta, and I talked about moving weights and controlling the U operator, and that's what these two steps are doing. So this step right here is what I conceptualize, meaning when I say I need to learn how to move weights, I need to move my coefficients as variables with respect to the weight. And this step, which relies on p-adic analysis on Banach spaces and the theory of compact operators on those things, this is what I mean by controlling the U operator. You can cut out something finite, a finite module, not an infinite dimensional one, so that UP essentially is acting through eigenvalues whose norm is not varying, which is the kind of thing that happens when you have a non-vanishing function on a rigid space, is that it's locally constant norm. This is my control of UP. Sorry. That's controlling the UP operator. I think in the mod P story, all I said was that UP was non-vanishing in the entire picture, which is kind of saying that it has norm 1 in the p-adic. Okay.
I have another question.
Yeah, please.
I guess I'm not sure I entirely see what the benefit is of constructing this V right now.
The V, okay, so I didn't even say how to construct the V for a minute. I should probably say that. So V then, once you have the MU, V is the spectrum in the rigid analytic sense of the image of the Heck operators acting on this M, which is some finite projective model. So to ask for what the benefit of V is, going back to this question, we need to look at my picture. So in my picture right now, I have this one blue line that explains one dimension of my Galois deformations, and I have some countable set of other points. And those come from the V. Like those points are points arising from V. Okay. Now you could just say, okay, forget about this entire part of the story. And let's just say I say the theorem that says, given F, there's some collection of F primes, right? Like I could just say part D and make up some congruences or something, and I would still get my yellow dots. What the V is going to do is the V is going to let me make little squiggly yellow arrows in there, the same way I did the blue one. Modular forms can only give rise to a countable set of points in deformation space ever, because there's only a countable set of eigenforms. V is something more like a p-adic ball that has an uncountable number of points, and it's going to let me fill in all the gaps in between those yellow lines.
Okay.
Okay. Are you sure? Okay. I know you want me to do more, but let me just say a word about GLN. Yeah.
In your picture, I mean, the W or the U is really some direction. The weight space. The weight space really in that kind of picture is some direction. And
Some direction in what? I mean,
it's really like a one-dimensional, it's a curve, the U if you want.
yeah, the U is a curve.
The U is a curve, and then the V is kind of finite over U, so it's a collection, a finite collection of each curve.
Yeah, yeah. I mean, you could take it to be some. It's like a branch cover of a curve in some sense. Except I drew it as an isomorphic cover of the curve.
Yes, somehow under this three-dimensional picture, there's a two-dimensional picture, right? Because the weight is in 2 dimensions.
Yeah, so that's right. I mean, typically in the references in the theory, I think so. What Malad is saying is like this blue line is like transparent when you construct the theory. And so typically in the theory, you kill the blue line from the beginning, and then the deformation space becomes 2-dimensional. And I've constructed a countable set of points in there. But I've constructed them in an orderly way. Like the U is giving me a guide for how these things are going to connect together through the weight of the modular form. But the physical object that the weight is tracing out is the V. Okay. GLN. Can you do this theorem for GLN? And the answer is yes. So I already mentioned a paper of David Hansen. And let me also mention a paper of Eric Irvan that's published in the Annals of Math. I think he might only have one paper in the Annals. He might have many, but there's only one that has the word eigenvarieties. So that's the paper. The weights, what I really want to do is tell you what kind of copying down you need to do, and then where you're going to run into some challenges. So the weights. The generalization of a weight of a modular form is like a character on the diagonal torus, like from Nadir's talks, except you take the ZP points. But this isn't that bad because that's just diagonal matrices that are p-adic units, and so there's n of them in dimension n. And so you just have lambda 1, lambda 2, lambda 3 that are lambdas like you already see. Okay. The algebraic ones are the ones that correspond to integers that have a decreasing or increasing order depending on how you normalize things. Distributions can also be copied. So you define I, N, I guess, from the Nadir's talk, is the Iwahori subgroup. So they're all the matrices G and GLN of ZP that are congruent to something like this, mod P. And then this breaks up, so that's an N. IN breaks up into something called N bar N across the ZP points of the upper triangular matrices, where this is, those are things that are not just upper triangular mod P, but upper triangular on the nose. And the N bar is 1 and then P times something in 0. So that kind of corresponds to the P. And that decomposition is not a decomposition as groups. This is related to the not, I mean, it's not the exact thing, but it's the kind of thing you have to worry about. The trick from the GL2 calculation and Raghuram's talk is this is a decomposition that's like p-adic manifolds. And when you do the group law, you have to learn how to conjugate things so that you can always put the products of two things here in a form like that. Okay. And this space here, by the way, the star creates an isomorphism with some number of copies of C. I guess it's n choose 2, which is how many things are in the star. I've done it right. Well, that is right. I think when n is 2, there's 1, so that looks good. And when n is 2, there's 1, and when n is 3, there's 3, which also looks good. Right, a 3 by 3 matrix probably has 3 lower triangular elements. You okay? Yeah, okay. And then the distributions on ZP in the GL2 story is like this piece of the Iwahori. There's one copy of ZP. They generalize to the distributions on kind of that, radical part. And then this has some action of a monoid. And this has some action of a monoid. And you can completely formally do these things. Okay. Now, let me just say aloud. No, let me write it because it's not fair to say this without writing it. Here. So in this theorem, you could start with now an automorphic form on GLN. That's a cuspidal eigenform that's cohomological, contributing to the cohomology. And you can construct a finite map over the weight space. The weights look like that. And a system of eigenvalues. And there's some U inside this monoid that'll make part A true. Part B, there's a tiny subtlety that Raghuram brought up. You see right here, I put a 1. You can't do this in a fixed degree necessarily, so you have to put a star there, and you take the eigensystems appearing anywhere in the cohomology. That's going to cause some chaos eventually. C is still going to hold, you're still going to interpolate what you want. D is going to be a problem. Okay, so A through C will still work. D will really only work under symmetry. So I'm not going to make that precise, but you'll see, I think, in Mladen's talk, an example where that's kind of happening. He talked about these kind of conjugate dual representations, essentially conjugate self-dual or something. And those are the situations in which you're going to get this kind of classicality results in the family, where you're going to have a dense set of classical points. And in general, you're not going to have that. And really, the bug in the issue actually goes back to here, and this I'm not going to write, is that in general, the eigenvarieties you're going to construct won't be over open subsets of the weight space, but things of positive codimension. So if I have time, I'll explain the issue slightly more, and we'll see what kind of Aladdin says. The next lecture. Yeah, please.
You have an unload of the map IR.
Yeah.
This calligraphic key to find dimension.
Yeah.
So you have to go to this E and var I to.
To algebraic represent, I mean, you have to specialize a weight at some point, like the monoid action has a weight. And when you specialize it to an algebraic dominant weight, there will be a highest weight representation, and there will be a map, an equivariant map for the monoid from the distributions to that.
I'll spend some time exactly on
Today or tomorrow?
that. No, today.
Raghuram's leaving tomorrow, so. Otherwise, it would have to be a dinner tonight, I guess. Good. So that's maybe some cultural information, or depending on how many open questions I talk about. Next lecture, something that I'll bring up again.
For almost eigenvariety requires geographic space series and infinity.
I don't think so.
Yeah. No, he's right.
No, I think Urbana eigenvariety just doesn't parameterize all cohomological eigenforms, but only those with non-vanishing or the Poincare characteristics, no?
That's some kind of
Derivative students. I think he's right, but Urban's strict like eigenvariety doesn't help, but the lemmas and propositions in this paper is intransposable and very useful. Strictly speaking, yeah, I mean, it's not applied.
Well, I think John is still correct. A and C still work for one, even if it's not a space series.
Yeah.
D doesn't, because it's.
But D doesn't work in general either. Like somehow Urban constructs something for every reductive group. What its properties are depends on what you call an eigenvariety. I don't want to get into exactly what you demand about part D in general. But to say for GL2, you get part D, and to say for GLN in general, you do not get part D.
If I may, like for the p-adic function, working in all degrees, it's a chaos. So
Yeah. Okay, so. The variation of Galois representation. So. Section on the proof and section on GLN, out of your mind, okay? Back to the pictures. Here, GL2 only. Still a theorem for GLN, proof completely different. But for now, GL2. So I let F U B be as in the theorem. Maybe I should call it theorem 1. No, I guess it's theorem 2. Then up to shrinking U or B, I mean, it doesn't really matter. So you can kind of see, I suggested that B comes from U anyway. Up to shrinking U, for every point B and little b, there exists a unique representation, rho B, of the absolute Galois group Q bar over Q to GL2 of QP bar, which is unramified and L not dividing NP, so the level of my modular form, my eigenform, and the determinant of rho B on the node is going to be, so the cyclotomic character is a character on the Galois group valued in ZP cross. I can then compose it with my weights of my point B, just like in my first talk, I talked about composing. And then because of, this is just so pedantic, like because of the normalization of the R versus the K, I have to multiply by the cyclotomic character. But do not worry about that second factor. The weight of the B gives you the determinant. That's what I'm saying. So this is a composition and that's a multiplication. And if L does not divide NP, then the trace of a Frobenius element at L will be equal to the value of the Hecke eigensystem on the TL eigenvalue lying inside L. And moreover, shrinking more, in fact, what do I want to say? Oh yeah, there's a whole representation. There's this rho v universal, so that's that's a big V from the Galois group valued in GL2 of let me just write this and then let me fix it next time if it's worried. I'm just worried about extending scalars slightly, but okay. Well, I'm just not worried about it. I mean, I took algebraic closures here because I'm worried about the rationality, and so I'm a little bit concerned about this, but functionally it's right what I've written. So there's a representation like this, also unramified at L different than NP, and at such L, the trace of the big representation on a Frobenius element is psi of TL now, right? So psi is the kind of global analytic thing. I saw a hand go up. Yeah, Vaughn.
Do you need to use the word say the word semi-simple somewhere?
Just insist that it's unique. Yeah, but it's actually continuous. I should definitely say continuous, and it's irreducible.
Oh, it's irreducible.
Yeah, so this is something that didn't come up so much because in the general PLN story, we know so little about this thing. But these Galois representations associated to cusp forms on VL2 are always irreducible. And that's what the shrinking is related to the irreducibility. I want to make sure that I am so small of a ball that everything is irreducible. Okay. And so now, going back to Henry's question about the V, so this V provides me now with a geometric space that's a one-dimensional object that has this entire Galois representation over the space. So the V itself, you can think of V as like a power series ring, and that power series ring provides a deformation in my deformation space the same way the blue power series thing provided a deformation. So what I can do in this picture, and I'll do it in a different color, maybe, is I can fill in this entire curve right here and call this like rho V universal.
You couldn't do this directly for D.
Hmm?
You shouldn't really do this directly for D, like need the extra points to live in D.
Yeah, I mean,
Okay.
yeah, I can't do it directly from you. I need the eigenforms at some point. I need the system of eigenvalues.
Okay.
You'll see, so I'm not going to prove this statement now, I'll prove it in the next lecture. And you'll see there that I'm really going to use this T. The T is the thing that corresponds to V, the Hecke algebra. But T is a Hecke algebra, and that's what gives rise to V. U is like just the weights. Okay, so now like I said, this deformation space is three-dimensional, and I produced somehow 2 dimensions locally at the origin. Somehow at the row F, I have 2 dimensions now. And they're really orthogonal. I'll explain that they're not intersecting with each other, at least as long as I'm small enough. Let me construct a 3rd dimension. And this will be a good opportunity to review something Mladen said, I think, out loud. And I'll just put it on the board for you. So this is the theory of twin forms, or the theory of refinements, that, as Mladen called it. In this theorem, I start with an eigenform of level NP. Okay. In this board, I'm going to start with an eigenform of level n. So let F be an element of Sk gamma 0 n now. which is an eigenform for the TL where L does not divide N. And in particular for TP, because P is one of those primes. Then I'm going to write x squared minus AP of x, AP of x plus p to the k minus 1 as x minus alpha, x minus beta. And then I'm going to set f alpha be f of z minus beta pz. Lemma f alpha is now an eigenform of level NP. Okay, that's the first point. The TL eigenvalue is the one I started with, the one from F, and the UP eigenvalue is the alpha that you chose. So the alpha is here and the beta is the thing you scale by. Okay. And this is another kind of thing I'll write the proof of on the board, but it is the kind of, I think I proved that complex Galois characters have finite image. The second proof I always remember is that calculation. And so I'm happy to explain it upstairs at some point tomorrow or today. Good. What do I want to say? So let me keep my pictures on the board. Doesn't want me to go over here. I want to keep the theorem on the board too. Because I want to emphasize something that just happened. I just explained to you, without saying it, how I can duplicate my families. Not duplicate, how I can create two families at once. You see, I start with an eigenform of level n. It's a single eigenform, and assume it's primitive in the sense of Eigenbaum's talk, that it's a new form at level n. So this eigenform has a Galois representation. Rho f. Valued in GL2. Well, I don't need to write out the whole thing again, I guess. It's a Galois representation of rho f. And my Galois representation, although I haven't said it precisely, I think we're starting to get the sense that that Galois representation is determined by the Frobenius eigenvalues away from the level. And you can even throw P away if you want. So it's determined by the TLs, where L is different than N and different than P. On the other hand, I have an eigenform F alpha at level NP. And F alpha has a family V alpha living over a weight space U alpha. Right? Because F alpha is an eigenform of level NP, and my theorem is about eigenforms of level NP. And I also have F beta and my family V beta living over some open set U beta. Are these open sets, U alpha and U beta, are just open sets containing my algebraic weights corresponding to K? So they can be the same. I can shrink them to make them the same. So what I really have in my picture over here is from an eigenform of level n. I don't just have this one V, but I have two different V's. Okay? And not only do I have two different V's, these V's are really different from the point of view of Galois representation. So here's the theorem. theorem 3. So at the beginning, I needed to assume that rho bar was irreducible. So assume F is in Sk now, gamma 0 n, and rho bar F is irreducible. Then in X rho bar, the three families one is the twist family. 2 is F the alpha universal. And the third is F the beta universal. They must intersect. They must intersect because they contain the row F. They contain the eigenform F already. The same as that they intersect only at row F up to shrinking. I mean, they intersect maybe in a finite number of points in any given neighborhood, and then up to shrinking the neighborhood, they intersect at a single point. So the picture becomes something like this. On this board, I specify that I don't just start at level gamma 0 np, but I start at level gamma 0 n. I construct my one twist here. This becomes my V alpha family, and then my V beta family is some third family coming into the picture. That's a completely new family. So these three families are going to define three different curves inside the deformation space. They're going to define three different tangent vectors inside the tangent space. And then for dimension reasons, they sort of have to locally at F fill out the entire tangent space. Up to some non-singularity issues that I do not want to get into. I was going to explain why this is true. Maybe I should do this. And then I'll say a little bit more. This is the start of an infinite Ferning process that we'll see if we have time to talk about. But I think I'm pretty close to. Maybe I could just explain the infinite Ferning. Yeah, I only have 3 more minutes. It's a lot easier to explain. So because all I've said right now is that if you start with an eigenform of level n, then you construct 3 families in the deformation space through the row F. So somehow locally, I've explained the 3 dimensions. I already know the space is 3-dimensional. I'm not trying to justify the space is 3-dimensional. I'm trying to explain the 3 dimensions. And I've only explained it locally at F. And this is where the V comes in again. Okay. Well, here's the infinite Fermi. So I start at row F. And now I'm going to just take the axes like I take over there. So this is one family. Did I use orange? Really read that. I'm sorry to everyone. That's hard to read over there. There's some orange family. This is like my V alpha. And there's some purple family. That's like my V beta. Right? But now my part D of the theorem. Okay, let's look at the V alpha family. And the V alpha family, I don't just have some random geometric object parameterized by weights or something like that. I have a geometric object V that at many, many points corresponds to a classical eigenform. On the V alpha family, there's some row G. G is one of the F primes, I guess. Maybe I'll call it row F prime. And it's not just there, it's like here, it's like here, it's like here, it's everywhere. Okay? Now out of this point, I have my twisting. one of the F prime families will correspond to the one that I already had. But at F prime, there's a check here that you have to make. At F prime, up to some finite number of exceptions, you're going to know that F prime doesn't just come from an eigenform of level NP, but come from an eigenform of level N through the twinning process. So F prime is really going to be some like F double prime alpha or some F double prime. And so that means that you're going to get another family through here. That's like the V prime prime beta or something like that, like the beta family for this new form. Okay, and now you log on to the Amazon cloud or something like that, and you tell it to propagate this as fast as it can. At every point, at every classical point along one of the V alpha or V beta families, you bifurcate into a new family. And you bifurcate into a twist family. And you do this over and over and over again. And what Gouveia and Mazur proved, hold on here. And Bergdall also, as part of this, so this is in the mid-90s and this is in the early 2000s, is that the process of the infinite Fern, I know I didn't define it carefully, but it's really something that you have to be shown and not written down. The closure of this infinite Fern is dense in extra one. Kind of as a p-adic manifold, if you like. And the only distinction between these works is Gouveia and Mazur proved the theorem in the case that you're kind of seeing on the board where there's like a 3-ball. And they only have to do it kind of at one point and then propagate it. And Bergdall did it in this slightly, in the more general case, where you don't necessarily know that your deformation space is literally the 3-ball, but it could have different components and things like that. And so kind of, I'll end here with that discussion. And I would suggest if you want to know why the 3 things don't intersect, that you ask, or we talk about it at coffee or something like that. So thank you for your attention. Say that again? So the references, and as I mentioned to a couple people, let me say this first. I do have references for like most of what I'm saying. And I'm typing up a small document with just the references in it, not the notes. And my plan is to then give the references to Andre, because I'm not very good at writing the references off. So back to your question, the term infinite Fern, I think, comes from Gouveia and Mazur. They wrote a paper in which they explained. So Gouveia and Mazur proved this somehow, this infinitesimal statement that I made about just locally at F, in the having 3 distinct tangent directions. They explained this before these families were constructed. But that can't get you this far, because to really get the closure of being everything, you have to really be able to propagate along real families. And that's really the V coming in somehow. And so they wrote a paper then explaining the infinite Fern once this kind of theorem had been proved by Robert Coleman.
It's one of the rare examples in mathematics where words really mean what they're used.
Yeah.
It really works a nice mental picture of people doing.
Yeah, their picture is better. I didn't draw them. I mean, what they would kind of draw one curve like that. That's like one of the V alphas. And then through some countable collection of points, you have crossing families. And then say on this one, you have another collection of crossing family, that's some countable collection of points, and you get this infinite, they call them spines and needles in the paper. I mean, Gouveia and Mazur wrote this series of papers from like late 80s to the mid 90s, and they're just like, it's like literature. You can really like sit down with a nice cup of tea, you can really read them. Whether you understand the mathematics is, okay, that's a different issue. What? You need coffee. That's like, the problem is I chose tea. Yeah, you had a question.
And this infinite burning process ever to like go up, go down, and come back around?
Oh, that's a
So I'm imagining a 3D grid that's given to like a fractal that keeps branching off.
Yeah, yeah, what do I wanna say? I have to think harder. I mean, it looks the way I draw the pictures like it can, but I think.
This is still like, this is a QP space, right? Not a like Mercury or something like that.
Not a what?
This is like a QP space, right?
As opposed to what?
Like I say, R3.
Yeah, it's a p-adic thing.
That
And so. So in the paper of Galois and Mazur, I know there's a section where they talk about the possibility that things are making cycles. Okay. But I forget whether they do it, I mean, they say like maybe this happens or maybe it doesn't. But they kind of suggest that it might, and then they explain how it doesn't cause any problems or something like that. Because you could worry that you don't fill out a dense space. You could worry that somehow I just keep going around in triangles or something like that. And they kind of, even if that happens, I think they rule it out. And they don't rule it out, but they explain that it doesn't matter.
Okay.
That it doesn't affect the density statements. What?
And it still ends up being dense, even if there's like.
Yeah, but they might explain why it doesn't happen, or maybe someone came along and explained that it does. I don't remember off the top of my head.
Okay.
Right now.
So when you're constructing this firm, you made this comment that even if the form in theorem 1 part C
Yeah.
the level at P, it actually does. And
Yeah.
this is such an incredibly useful thing in various different things that I wanted to highlight. And here's a very simple concept.
Should I explain what happened? Or go ahead.
Tell you the concept.
Yeah.
Remember, on Monday, there was this example with x0 of 11. And there, the U was restricted to weights which are congruent to 2 modulo 10. Here's why you cannot have a bigger U than that. In theorem D, if let's say that U was everything, so you're not restricted to weight 2, weight 12, weight 20, and so on. You take weight 3. Because in D, the modular form would then have not have anything that's E. It would be a weight 3 modular form of level 1. There's no such thing. So somehow this U, you keep shrinking the technical reasons, but it also just cannot possibly be too big because then D. It's a very nice concept.
Yeah, I mean, I
It's a
should,
very useful thing that this is doesn't these modular forms in D don't have level other than the first.
there is a step that it didn't explain as well as I would have liked.
Sorry, you're saying that you would, why would it have no level at P? Or are you just saying that these twin forms
I'm
would show
saying
up?
that if you start out with the modular form F, which has level of P, that imposes the local representation of this time word.
Sure, yeah.
And because of part A, that puts some condition on valuation of heck eigen.
Okay.
So if there, and that depends on the weight itself. In a different way, anything R prime different from R, that cannot possibly be this. Have to not be time word. Have to be.
Yeah, let me just write on the board. So I made this comment that at level NP, you never have a non-zero eigenvalue. So 2 reasons why that happens. So a form at level NP can arise in 2 ways. It can be a new form at level P, which is to say that the automorphic representation has Iwahori invariance and not GL2 invariance. If it's a new form, so it's in the P new part, we call it, then the AP of F can only be one of 2 things. It can be plus or minus e to the k over 2 minus 1, and I can look at that and see that they're non-zero. Right? So the things that are new at level P look like this, and the valuation of the AP is some fixed number that depends on the k. Okay? The other thing that can happen at level NP is you can come from level N through this twinning process, in which case your U eigenvalue is one of these 2 numbers. But those 2 numbers are non-zero because their product is p to the k minus 1. Okay? And then what Andre is pointing out in this family is the way you rule out the new form thing is like this F has this V alpha family, and everywhere in the V alpha family, the AP eigenvalue has the same norm as alpha. So that's some fixed number. But in the family, the weights are like p to the billion now. And so p to the billion minus over 2 minus 1 is probably not the norm of alpha. And so you know that you're not arising from the new form theory, you must be arising from the old form theory, and that allows you to branch in the other direction at the other form. Like it's something fundamental about the way that p-adic analysis allows you to have these constant norms in p-adic families in a way that complex analysis does not. You can't construct complex functions with constant norm. Well, you can, but you can't do it all the time.
In this V, so sorry, were you saying in this V alpha family the UP eigenvalue is or it's varying, it's also varying p-adically is what you're saying?
The UP eigenvalue is varying p-adically, but its norm isn't, right? So the UP eigenvalue, part A says the UP eigenvalue over your V is non-vanishing. So, and a non-vanishing continuous p-adic function has constant norm on a small ball.
Sure.
And so up to shrinking V, which I can do when I'm doing my propagation process, I can just assume that over all of V alpha, my UP eigenvalue has the same norm as alpha. Which means to avoid the new forms, I have to rule out just one weight, because I know exactly what norm I need to avoid. And I can do that again by shrinking slightly more if I need to. There's a lot of numerics that go into this that is like understandable things. And so I encourage you to like look at the papers and stuff like that. Really kind of grapple with exactly the logic. Because you learn a lot of things, like people that do smooth representations of p-adic groups know these numbers off the top of their head, and I kind of learned it through doing these exercises and understanding. So. Thank you again.
Yes,
You have to leave though, right?
I will.
Yes.